Hi, welcome to the talk on delay-aware backpressure routing using graph neural networks. I'm Zhongyan Zhao. This is a collaborative work with Boyan Radoichi, Gunjan Verma, Ananthan Swamy, and Santiago Segura. Backpressure routing is a routing scheduling scheme that has been proposed for multiple multi-hop wireless networks. This type of network has been conventionally used in wireless ad hoc and sensor networks, and more recently applied for wireless backhaul networks for 5G and 6G, as well machine-to-machine communications in Internet of Things. So it is an important algorithm for modern communication system. In backpressure routing, wireless network is represented by a graph, where each node is a wireless device and each edge is a wireless link. So each node will host the per destination queues. Basically, the packets in each queue is referred to a commodity. The routing is conducted in 4 steps. First, we're going to select the optimal commodity for every link. So this optimal commodity will maximize the differential queue length on that link. Then, we're going to find the link gradient based on this equation, and then we run a max weight scheduling that will select a set of links to be activated at time t. And the capacity of those links being scheduled will be assigned to the optimal commodity on those links. So this type of routing has these advantages of it has a fully distributed execution, it can prevent congestion automatically, and it's also throughput optimal. It also has some drawbacks such as slow start. It will form some loops. There's a last packet problem we will introduce later. So basically, to address this kind of problem, we have proposed the biased backpressure, where on top of the queue length, we're going to add a shortest path aware bias for every commodity. So here we use an example to illustrate the difference between the basic and the biased backpressure routing. So in this example, we have this wireless network and the flow from the source to destination. And the simulation runs 500 steps. So in these 2 examples, everything is the same except the routing algorithm. With the vanilla backpressure, we can see that the routes only reaches to here after 500 steps, and there are some loops that is obvious. Basically, packets being transmitted back and forth on this link, and no packets reach the destination in the 500 steps. However, with biased backpressure, where the bias is the shortest hop distance from each node to the destination, we can see that 2 routes is being formed on this graph to the destination, and the packet obviously reaches the destination. So biased backpressure could address these 3 drawbacks of vanilla backpressure. The question is, can we do better than the shortest hop distance bias? What we propose is delay-aware shortest bias based on link duty cycle. So link duty cycle is the value between 0 and 1 that measures how likely a link is scheduled under current network topology and traffics. So instead of treating every link equally, we define per hop distance as the inverse of the link duty cycle, or proportional to this. Right. For example, in this network, we have a flow from the source to destination. If we rely on shortest hop count distance, then we will prefer this route. However, these 2 links has a low link duty cycle because they have a lot of conflicting neighboring links. Based on our approach, we then would prefer this route because this has a shorter distance. So in practice, we use graph convolutional neural network to predict this link duty cycle based on the conflict graph of the network. And this approach maintains the fully distributed execution of backpressure routing because GCN has fully distributed execution. Our approach has some good properties. First is the low additional complexity. So basically, we need to run the GCN and the all-pair shortest algorithm. The first has a constant complexity, and the second has a linear complexity to the size of the network. Moreover, these overhead can be diluted over time step because they only need to run only when the topology changes. Our approach also keeps the throughput optimality of the backpressure routing. So the training of the GCN can be done in 4 steps. First, we're going to draw a random network instance that include the network itself, the random flows, packet arrivals, and link rates. And then based on these, we run the GCN to find the per link distance x. And based on this x, we run the APSP to find the shortest path bias b. And with this b, we run simulation for many time steps. And we collect the empirical schedule of each time step s, which is a binary vector of size of the link, number of links. At the end of the simulation, we use this loss function, basically the mean square error between the x and the average empirical schedule to optimize the GCN. And we repeat this process until the GCN converges. Let's look at the test results. We run the simulation for test on 100 random graphs from BA model, and the time steps is 1000. We compare our approach with vanilla backpressure and other biased backpressure based on hop count distance, and also with access to the link rate. Right. Our approach performs better than those benchmarks given the same access of information. So this test is on the interface conflict model, which simulate such as millimeter wave networks, which has a lower conflict degree. When the conflict degree increases, such as under unique disk conflict model, representing wireless sensor and ad hoc networks under omnidirectional antennas, the delay of every algorithm increases, but our approach still maintains the best. Finally, we compare the delivery rate of these algorithms under different traffic load. We can see that as traffic load increases, our approach maintains the highest delivery rate. To sum up, in this work, we use graph convolutional neural network to predict the link duty cycle and then use it for biased backpressure routing. So compared to the shortest hop distance bias, our approach can significantly improve the end-to-end delay and the delivery rate, while keeping the advantages of fully distributed execution, simplicity, low overhead. We hope that our approach can also be used to improve other routing schemes. Thank you for listening. Please check out the paper for more details.